Microsystems Technology Office Deputy Director, Dr. Dev Palmer.
ERI is all about bringing the microelectronics community together. But we're looking for more than a meeting of the minds. We're looking for impact. And as you will see over the next few minutes, great results come from great partnerships. In the early days of the United States, agriculture was the dominant industry. It provided for the immediate needs of the relatively small population and even provided surplus for export. But there was a growing concern that agriculture, while necessary, was not sufficient to support the growth and expansion of a new nation. That's why in 1791, Congress tasked then Secretary of the Treasury Alexander Hamilton to produce his famous report on manufactures, which stressed the importance of government-industry partnership to spur innovation. About 50 years later, it was congressionally appropriated funding that helped demonstrate the feasibility of Samuel Morse's telegraph, which in a way was the first step to the networked world we find ourselves in today. Government requirements pushing innovation, combined with the productivity and broad market support of industry, led to dual-use technologies of great military and commercial benefit, including interchangeable musket parts, the first radios and radars, engines and airframes, and the first computers. While we're thinking about the future of microelectronics, it's fun to look back at the early breakthroughs. At its time, ENIAC was a technological wonder. It had a smoking 100 kilohertz clock, used only 150 kilowatts of power, and fit in a compact 30 tons comprising a 150-foot line of racks. But even with all that size and power, you'd be hard-pressed to find a calculator or a computer today with as little processing power as it had. It could store only 20 10-digit numbers, but it could do 5,000 additions or 14 10-digit multiplies per second. The partnership between John Mauchly and J. Presper Eckert was the engine behind ENIAC, just one of the many dynamic duos in science and engineering, such as Pierre and Marie Curie, who discovered radiation, James Watson and Francis Crick, who defined the structure of DNA, and John Bardeen and Walter Brattain, who discovered the field effect transistor. They say two heads are better than one, and there are many other examples of great partnerships that prove it's true. When ERI started in 2017, the primary stated goal was to form partnerships between government, industry, and universities to spur innovation that serves the needs of both the defense as well as the domestic commercial sectors. 3 years into the program, we're already seeing some amazing results. ERI Performer Arm was part of the N0 program to develop ultra-low power sensors. The resulting ARM M0N0 processor has a shutdown power of 10 nanowatts and an active power of about 50 microwatts per megahertz, depending on the application. That shutdown power, combined with the low-power read-only memory for program storage and low active power, enables mission lifetimes that are limited by battery leakage, many months, perhaps multiple years for conventional coin cell batteries, which will accelerate the promise of untethered systems and Internet of Things devices to an achievable state. But wait, there's more. ARM has agreed to make 1,000 licenses available to government and government-sponsored researchers at a reduced cost to explore applications in power-constrained environments. A recent collaboration between DARPA and Microsoft in support of the DARPA System Security Integration through Hardware and Firmware program also has generated interesting results. Teams from SRI International and the University of Cambridge used their Capability Hardware Enhanced Risk Instructions, or CHERI, approach that extends the hardware instruction set architecture to enable fine-grained memory safety and scalable software compartmentalization. CHERI has been demonstrated on MIPS, ARM, and RISC-V instruction set architectures and is being considered by a number of commercial transition partners, including Google, Apple, and Microsoft, for deployment in applications ranging from embedded systems and mobile phones to high-performance servers. In partnership with DARPA, the Microsoft Security Response Center evaluated secure processors from the SITH program. The 5-week Red Team exercise determined that SITH hardware would mitigate more than 70% of all of Microsoft's vulnerabilities reported in 2019. Currently, Software security patches incur an estimated 20% performance overhead penalty in the Windows operating system, and computer systems are the most vulnerable between the identification of a vulnerability and installing the patch update. SITH hardware technology will significantly reduce the need for software patches and updates, making computer systems not only safer, but also faster. The CHIPS program has created an ecosystem of discrete, modular, reusable IP blocks, which can be assembled into a system using existing and emerging integration technologies to enhance overall system flexibility and reduce design time for next-generation products. The team from University of Michigan teamed with Intel to take advantage of this new capability. Leveraging existing chiplets in the Advanced Interconnect Bus standard, they produced their own microcontroller unit in 16-nanometer FinFET CMOS and demonstrated 64 gigabits per second data transfer to a Stratix 10 FPGA over an embedded multi-die interconnect bridge. This amazing accomplishment demonstrates the ease and versatility of modular 2.5D integration enabled by CHIPS and the partnership between academia and commercial industry. The Trusted and Assured Microelectronics program, managed through the Office of the Undersecretary of Defense for Research and Engineering, supports microelectronics modernization activities that enable defense systems to keep pace with commercial microelectronics technological advances, reduce reliance on obsolete microelectronics, and mitigate the department's reliance on sole source foundries for assured state-of-the-art microelectronics. DARPA is partnering with TNAM on projects supporting new microelectronics development, demonstration, and capability insertion, including supporting public-private co-development. DARPA and AFRL teamed with Global Foundries to jointly fund a manufacturing run in an advanced node to generate quantifiably assured manufacturing data that can be used to validate and improve assurance tools for advanced semiconductor designs by comparing simulation results to hardware measurements. Stay tuned for more results as these projects progress. So 229 years later, we can say that Hamilton got it right in his report. It is critical for government, industry, and academia to form productive partnerships that are the underpinning of the wealth, independence, and security of the United States. Enjoy the rest of the event.
And now, our featured Fireside Chat with the CEO of ARM Limited, Mr. Simon Segars. Mr. Segars is joined by the Executive Director and Chief Operating Officer of IEEE, the Honorable Stephen Welby.
I am very pleased to be with you here today. I'm currently the Executive Director of the IEEE, the world's largest organization of technical professionals. I've had a long association with DARPA as an investigator, as a DARPA program manager in several offices, and as an office director in several offices at DARPA. And of course, in my previous role as Assistant Secretary of Defense for Research and Engineering, where I served as the Chief Technology Officer of the department. I'm really pleased today to be joined by Simon Segars, the Chief Executive Officer of ARM Holdings, the world's leading semiconductor IP company. ARM is a global leader in the development of semiconductor technology and is central to the pervasive computing that is shaping today's connected world. Processors based on ARM architecture families make up over 90% of today's market for mobile processors, over 90% of the processor market for IoT applications, over 75% of the market for in-vehicle infotainment and driver assistance processing, and are continually growing their share of networking equipment, data center, cloud, and desktop computing sectors. Since its founding in 1990, ARM has really been a remarkable business and technology story. And so Simon, thanks for joining us today, and I really appreciate having the chance to talk to you.
Thanks, Stephen. It's a pleasure to be here, and thanks for that introduction.
Well, I'd really like to just get right into a conversation today about some topics that are central to the DARPA Electronics Resurgence Initiative. Simon, the first thing I'd like to ask, you've described our current moment in technology as being the beginning of a fifth wave of computing, one driven by the convergence of the demands of 5G, of IoT, the Internet of Things, and artificial intelligence. What technology and business trends do you see reinforcing this idea of a fifth wave of computing? And perhaps, how do you see it impacting the commercial and government technology sectors?
Yeah, thanks. I mean, when we look back over the history of computing, I think there have been moments in time when technologies have appeared or have come together which have really driven phases of growth in technology, and that technology has helped drive economic growth. And so, moving from the mainframe through the PC and the kind of advent of the software industry that grew around that, through the advent of the internet and then the mobile internet and the cloud, we now find ourselves at a point where the technologies that you just mentioned, IoT, AI, 5G, they're coming to a kind of maturity at the same time. And I think while they're interesting in their own right, it is the combination of those technologies that really do open up new opportunities. Through IoT, we're going to be able to sense what is going on in the world. Through 5G networks, we're going to be able to connect all of these sensors together. And then through using the power of AI, take the data that comes from all of those sensors and actually extract information from them so that we can find out what is going on in the world. So each of those technologies, as I said, interesting, but when you put them all together, you kind of look at that and think, wow, this really is a kind of new era, a new wave of computing that will open up just huge opportunities commercially, within governments, within the defense sector, just across society. And almost wherever you look, when you think about how food ends up on our table, how healthcare is deployed, how education is delivered, especially in this world of staying at home and dealing with COVID-19, these technologies, I think, are really going to come into the fore as they are actually deployed in the field, and we just see it happening faster and faster every day.
Well, as we see these technologies playing a bigger role in everyday life, a bigger role in government and in the private sector, we've seen the U.S. government starting to take notice, and DARPA and many other agencies have been working together looking at a U.S. national strategy with respect to these technologies, particularly with respect to 5G, and also more recently, perhaps, with respect to the larger semiconductor industry. A lot of that discussion has been driven by concerns about economic futures and about national security and what role the government should play in shaping those areas. I wanted to ask what you think a smart U.S. industrial strategy might look like, and perhaps how you think that such a strategy might impact both the domestic commercial sector, the defense and aerospace sector, and perhaps outside the U.S., our allies and partners.
Yeah, I think what the last 20 odd weeks that we've all been working from home has really brought sharply into focus is just how dependent we are on technology to run our everyday lives. And underneath all of that is our semiconductors and computing. And our business, as you mentioned right at the beginning, has grown really through the growing needs of, or the growing opportunity that comes from deploying microprocessors, tiny computers in all different areas. And that is just set to grow and grow. So in an industrial policy, as you think about where that takes you, you have to think about the underlying technologies, the science that drives the next kind of evolution of all of these technologies. And that is an area where I think governments can play a big role in helping stimulate research, because this stuff is really hard. And so many companies are focused on, as they should be, delivering products, generating revenues, generating profits. That's what companies are there for. Some of the core R&D that has to happen underneath this, though, is long-term. The exact monetization of it is not obvious. How it's going to get turned into product is not obvious. And I think at the core of any industrial strategy for the government, it is key that investment in R&D plays a very large role. Around that, then you have to think about how does that raw R&D get commercialized? How is there technology transfer happening to companies that can take that raw R&D and actually exploit that commercially or through defense or government sectors? And then what's also really important is to think about the skills that are involved. What we do is really difficult, and you don't replicate what is done just by throwing money at the problem. It does involve people with the right skills, the right educational background, the right experience, the right environment for them to learn from others who've been doing it a long time. So I think making sure that the right skilled people are available to work on this research. They're able to go into raw, kind of go between raw R&D and into companies and back again. That the environment is there for people to be mentored and have their skills developed. Because you have to really think about the long game that needs to be played in the development of technology. It does take a long time. And so new technologies are evolved over a long period, and technology leadership is lost over a long period as well. It's something that you just can't ever let go of. You've got to keep ensuring that the right environment is there for this to keep growing.
So I heard you say both kind of building foundations, supporting transition, and then talent, the importance of talent in all of this.
Yeah, absolutely. I mean, talent at one level is kind of all that matters. As an IP company, we don't manufacture anything, we don't build things. It is all about our people. There's about 7,000 people in ARM. And with my management team, we spend a lot of time just thinking about how we're attracting people, how we're developing them, how we're retaining them, how we're making sure that they want to stay in ARM for their careers. Talent is absolutely critical.
Simon, I've heard you in other forums discuss one of the main themes of ERI, and that is the constraints that we now face with the run out of Moore's law. The fact that it now takes an enormous effort to come up with something that's going to deliver more performance, more power efficiency, a better price point each year. We've gotten addicted to that kind of yearly cycle and that continuous ever upward capability that we've been able to see from semiconductor technology. And that's, of course, empowered so much of the technology change that we've seen. As it becomes more difficult to deliver on that expectation of continued upward growth in capacity and capability, how is ARM addressing these kind of new emergent architectural challenges? And how might things like chiplets or other architectural changes help us drive the cost, performance, complexity curve forward into the future?
Yeah, the advancement in semiconductor technology over the years has just been phenomenal. I mean, I've been working for about 30 years, and I remember people saying to me in the early days, Moore's law is going to be over, and I don't know what we're going to do after that. But it is just unbelievable what the world's technologists and scientists have been able to do in just keep driving transistor scaling down. Things like the evolution of FinFET, it's just incredible. When you look at the pictures of those transistors, under the microscope, it's just incredible what can be done. But physics gets in the way. There's not much you can do about that. And there comes a point where you just can't keep scaling transistors anymore. So you have to get really creative when it comes to architecture, how you use those transistors, how you develop circuits and parallelism that keeps driving performance. And then the next step ahead for us looks like moving into the third dimension. So people are building today chips utilizing chiplets. So individual die, which might be on very different technologies, integrated into a single package on a substrate with connections between them. And probably some of the switching circuits that is connecting you and I today are using this technology right now. So that's there. It's very hard to use. It's not a very commonplace technology, but it is out there. So we think in the next kind of twist of this, we need to make that an easier technology to use. And there's work that we can do from the design front, the design methodology front to help with that. And then stacking die on top of each other provides another really interesting route forwards for us to be able to put effectively more transistors into the same space and deliver more performance. And there are different ways in which you might look at that. You might think of putting, literally just sticking a memory die on top of a logic die with an analog die on top of that. Again, people have done it. But what's interesting is to think about, well, can I put lots of small die together? Semiconductor yield is basically inversely proportional to the area of the die. So if you can make lots of small die, stack them together, then you can get better yield than if you just build some big monolithic die. But again, you have to rethink the architecture to exploit parallelism and find ways to deliver performance. But this ability to go vertical, which again can be done, it's very hard, but it can be done. If we can simplify that, if we can make that a common way that people design chips, then I think it's going to unlock another dimension of performance. And ultimately, Moore's law is while it talks about transistor scaling and sizing, and you've got Dennard scaling as well, ultimately what we're trying to do with each generation is provide more performance at better or lower power. And just scaling transistors isn't necessarily the only way to do that. We're going to have to get more creative. We're going to have to develop new technologies. Back to the industrial policy, thinking that through and thinking through what that looks like in 10 years' time, making the investments now. That's the important thing to do. But I do think this kind of vertical scaling does represent a really interesting way to deliver more performance.
I'm really struck that there's really two dimensions to that response, right? One about design and how we can begin to rethink applications into these kind of processes. And at the same time, the complex manufacturing associated with being able to assemble
For sure.
the heterogeneous components, interconnects, and all the challenges associated with 3D integration. So.
Packaging die is a kind of it's something people kind of take for granted. But actually, if you're taking a heterogeneous die that may have been manufactured in different places, you're going to put them on top of each other. They're going to talk directly to each other through the silicon substrate. You're going to put that in a package and deal with the thermal effects. That is a non-trivial problem. So it isn't just about transistors. It's about how all of those technologies come together and deliver a system that works.
Let me talk a little bit about delivering systems that work. One of kind of the fundamental tools of engineering is standardization. And Simon, today ARM is, I know, leading a number of industry efforts working towards developing standards, in particular standards around security for interconnected systems. This is a very hot topic at the moment. And in fact, recently the US Congress has directed DoD and through DoD DARPA to play a larger role in shaping technical standards in areas like supply chain protection and cybersecurity, which all interact with complex areas like technology export control and concerns about trust in systems. Sometimes we see this this kind of conversation set up as a competition between interests, between the interests of the commercial sector and interests in government. And I wanted to ask, how can commercial standardization efforts and government standardization efforts work together better to help maximize success for everyone?
Yeah, it's a really complex topic because security is probably one of the least well-defined topics that there is in technology. When people say, I've got good security or bad security, what does that actually mean? The fact that there is no good way to measure security, and it is quite amazing just how ingenious bad people can be when they're trying to hack into systems. It's a changing landscape. So, we've kind of looked at this and been thinking about it for a long time, and especially with the advent of the Internet of Things and the glory that having billions of connected things in a 5G network brings. Well, the side effect of that is that's a billion ways in which some bad actor might get into the system. So, when you couple this with the fact that there's no good way of expressing security and the quality of security, that's a real problem. You as a consumer can go into a store today and buy something that you hook up to your home Wi-Fi network. You have no idea whether the engineers that worked on it spent 5 minutes thinking about security, 0 minutes, or 10 lifetimes.
That's really the core question. Should I trust? Right. That's from a consumer perspective. Should I trust this device? Right.
Yeah. And I think some standardization in the way in which security is expressed is really, really important. An analogy I often draw is with car safety. So, the car industry grew. There were no standards around how to make cars safe. Consumers, got injured along the way. NHTSA came along in the 70s, and then in the 90s created the crash test rating. And now anybody watching this stream, when they go and buy a car, I'm guaranteed they're going to look at that crash test rating and go, okay, 5 stars is good. 1 star, I don't want to buy this product. IoT device or anything that you connect to a network ought to have something like that, where you can look at it and say, okay, this score tells me just how thorough a job has been done around security. Now, behind that, you need to do a lot of work. When you think about security, one thing that quickly becomes apparent is you need to define what you're secure against. So there's this whole concept of threat models where you can say, I'm secure against these things. My house is secure, but only if somebody tries to get in through the front door. If they stick a brick through the window, it's not secure. So the threat model that the door lock gives is against somebody trying to pick the lock. Well, similarly in electronic systems, you need to define threat models. You need to then provide testing frameworks so that you can check against them, and then you can provide the consumer, whether it's consumer, or whether it's a government, or whether it's somebody in the defense sector, they've got a way of understanding what it is they're actually buying, what risks they're taking in using this product, and therefore how much trust they've got in it. And it is that point you mentioned, trust, that is ultimately what matters here.
It's interesting to see the role that standards do play, though. They allow us to build ecosystems more than just kind of individual companies or individual organizations' approaches. They allow us to kind of work together to build frameworks that support a larger community, right?
Absolutely, and it accelerates industries, and it enables industries to build around others. So on that standardization work, and I know the IEEE plays a huge role in helping develop and maintain standards. It's super important. Around this area of security, we've been trying to pull together other companies who have a vested interest, not just other IP companies, not just chip companies, but people who are then going to be writing software that runs on top of these devices, systems companies, because delivering a secure product at the end of the day isn't just one person's task. It is the combination of efforts of people across the entire supply chain that need to come together. And so we've been trying to bring communities together. Our PSA work that we've done, our platform security architecture, that was a first step, creating a set of frameworks where we've said, we think if you build embedded devices like this, then you can then build software on top. We've defined some APIs, so there is a way of accessing resources that are on the chip in a standardized way. And that just helps people with testing. It helps people with product development. It accelerates that. And again, just means that what's out there isn't just a complete a random collection of things which are going to have different ways of being exploited. So it's a work in progress, but PSA has been very successful. There are different levels of certification you can achieve. We've brought on third-party labs to work and do that certification. So it's not an ARM thing. It's we're trying to really turn this into an industry thing.
Well, let me ask then for our last topic today. I know that our audience at the ERI Summit is made up of researchers, innovators, aspiring entrepreneurs, and technology policy leaders. The audience is really full of people who are hoping to shape the future and consistent with DARPA's mission, who want to create technological surprise, who really want to move the ball far. How can someone with a good idea bring it to fruition, leveraging the kind of technology that ARM provides?
Yeah, it's something we're absolutely aligned on wanting to have happen. I've got to say, in my career at ARM, and I joined the company right at the beginning, it's been the number of times I've been pleasantly surprised where someone has done something using our product that we just never thought of. The applications that have emerged weren't what we were thinking of in the first place. And it really does highlight that when you can package technology and put it in the hands of people with smart ideas and enable them to use it easily and avoid them having to reinvent the wheel the whole time, you just get more innovation. You just get invention that comes from that. So as we've seen the semi industry evolve, we've been evolving our business model and trying to find ways, especially of late, of just lowering the barrier to getting access to ARM technology. We want people to innovate. Whilst the cost of manufacturing on the leading edge is really high, there's a lot of manufacturing you can do at very low cost. So we want to make our IP available. So we've changed our business model. We have a program called Unflexible Access, which makes it very easy for people to get hold of a wide range of our technology for very, very low upfront cost. They work out what they need, and then they work out what it's worth at the end of their design project. So you don't have that barrier in the way. And we put together a program specifically with DARPA to enable the DARPA community to get access to our technology in this way. There's an amount of prototyping people can do. For universities who are sharing their research, it's even easier and even lower cost to get access to the technology. So we want to make that happen. We've partnered with DARPA to enable that DARPA community to get access to what we do, and we're looking forward to seeing some great results coming out.
That's super. I hope that we see some future industries born out of the collaborations that we might see from this prototyping work.
Absolutely, yeah. As I say, I'm surprised on a regular basis at just what people build. When you put the tools in the hands of smart people, good things happen. And our job is to sort of try and get out of the way. Make it easy, make the products easy to use, build an ecosystem so that there's software tool chains available and third-party support and design service. Just enable an ecosystem and then get out of the way and see what people build on top of what we've done.
Well, on that note of making good things happen, Simon, I again want to thank you for joining us today at the ERI Summit. I want to thank you for this great conversation, and I look forward to seeing you in person rather than virtually one of these days.
I hope we can do that. It's been my pleasure. Thanks very much, Stephen.
Okay, take care.
Thanks.
Good morning. My name is Richard-Duane Chambers. I am the Special Assistant to the DARPA Director for ERI. As we were planning the summit, we were very fortunate to have the opportunity to engage with Ms. Nicole Petta, the Principal Director for Microelectronics, sitting within the Office of the Undersecretary of Defense for Research and Engineering. Prior to joining the DoD, Ms. Petta was the Special Assistant to the Director for the Laboratory for Laser Energetics at the University of Rochester, and the Division General Manager of Schaefer Livermore Laboratory before that. We sent 4 pre-recorded questions to Ms. Petta and received her pre-recorded responses. So to start off, Ms. Petta, welcome to the ERI Summit. Your role as Principal Director within the department is relatively new, but I understand that there is a relationship between the 2018 National Defense Strategy, the department's decision to establish modernization priorities, and the creation of the Principal Director roles. Can you help me and the ERI audience to understand the relationship between the National Defense Strategy and your responsibilities as Principal Director?
The National Defense Strategy placed a large emphasis on modernizing the force. And one of the results of the National Defense Strategy was 11 modernization priorities across the department. Each modernization priority is assigned a principal director. So we are essentially the portfolio managers across the department for that particular technical area. My boss, Dr. Lewis, would call us the belly buttons for the department. So if you have an issue, there's one focal point that can help you solve your issue, and we're really responsible to look across the entire Department of Defense and put together modernization roadmaps And these are meant to quickly address the technical challenges that each of us face. We're responsible for resource recommendations and consolidation of resources to achieve those objectives, and really just making sure things run fast and efficiently and are pointed in the right direction. We work with the services very closely throughout the Pentagon and our partners, other government agencies, academia, and of course, most important, the commercial industry, which really drives the microelectronics market.
Over the course of the ERI Summit, our audience is going to hear a lot about various technical microelectronics challenges facing the industry and its customers. What challenges are you focused on, and what's the department's path to addressing them?
DoD is addressing technical challenges through the execution of the microelectronics roadmap. For the purpose of this conference, I will frame parts of the roadmap in terms of competition, security, and ensuring against supply chain disruption. In the near term, we're focused on competition and security. So the department must get access to the capabilities that already exist onshore. We need multiple suppliers and competition for critical technologies that the department uses. Lack of competition can lead to poor quality, schedule, and cost. Second, we want to have mobility to move from different foundry ecosystems. So we're developing IP in various foundries to make sure that we have competition across the Department of Defense. In order to do that, we have to invest and develop new security protocols with measurable security to enable the department to get access to the very best technology and get and stay on the commercial curve. We're replacing outdated security protocols that relied on perimeter defense with assurance, with quantitative assurance, and these will be instantiated in the standards and the update to the NDAA per the NDAA. So we're working aggressively on meeting that objective of defining security quantitatively through standards. This new strategy and approach is quantitative assurance based on zero trust principles. This represents an important shift for the department. Trusted foundries, though useful for some applications, are not compatible with the leading edge, bleeding edge fabrication facilities. And so we're working aggressively to update those policies and quantitatively measure the security in our supply chain and not rely on perimeter defense. And we believe our interest to protect our IP, the confidentiality of our designs and the integrity of designs are aligned with commercial interests. So we're partnered closely with commercial, whether you are a fabless semiconductor company or an EDA tool vendor or a manufacturer of tools in the line, or the foundries. We're partnered broadly across commercial to capture data and best practices, both to ensure the confidentiality and the integrity of our supply chain. The third is ensuring against a supply chain disruption. So there's ample capabilities onshore right now to meet the department's near-term needs, but in the long term, we have to ensure a supply chain in the United States with our U.S. companies and our allies. And the move offshore was largely driven by commercial, so we're thinking a lot about how to incentivize both the foundries and the users of foundries to invest in critical manufacturing onshore in the United States. And we're working with key stakeholders across the department and government and industry to define and solve over the long term this difficult issue. We're excited about the progress that we're making and look forward to continuing to work with all the stakeholders on that issue.
At this point in the summit, I expect, and I certainly hope, that many in the audience would have heard a bit about this concept of quantifiable assurance, sometimes called quantitative assurance. Can you help us to understand, Ms. Petta, what is quantifiable assurance and what will this mean for DoD programs?
At the simplest level, we're moving from qualitative trust to quantitative assurance. So we want to be able to measure whether it's the design, fabrication, or packaging. We want to be able to measure and quantify both the threats, the countermeasures, and the residual risk. And we're doing that through the use of attack countermeasure analysis. In close partnership with the Joint Federated Assurance Center, DoD users will have threat-specific plans for their unique program. Some programs have very low risk tolerance, and others getting access to the very best technology. That in itself, it's a risk not to have access to that technology. So the intent with quantifiable assurance is to create a flexible, threat-specific approach to the DoD requirements and open up access to the very best technology with measurable security.
And finally, Ms. Petta, thank you so much for joining us. We really appreciate your time. To close out, cooperation between the commercial, defense, and academic sectors is one of the core tenets of ERI. Can you give our audience your perspective on partnering with the commercial sector and what role ERI may have in that?
Whether it's meeting our objectives for competition, security, or ensuring against a supply chain disruption, we believe it's critical for the government and the commercial sector to continue to work together to address these shared challenges. We believe our interests to protect both the confidentiality and the integrity of our supply chain are aligned with commercial interests, and we'll continue to work across government and commercial industry to develop and implement our quantitative assurance strategy based on zero trust, as well as informing the NDAA standards development. We'll work together long term to establish an uninterruptible supply chain for critical infrastructure and the Department of Defense and government that can flexibly respond to the changing demands and unexpected crises. We will continue to invest in research and development to ensure that the U.S. stays ahead and can run faster. And ERI is foundational to that work. I'm excited to be part of ERI, and it's an exciting time for microelectronics in the United States. So thank you all for your time, and enjoy ERI.
This begins the morning break. The plenary session on heterogeneous 3D microsystems will begin at 11:45 a.m. Eastern Time.